Professor Shiteng Zhao.
Hi everyone. It's also my honor to have this opportunity to host now Professor Shiteng Zhao's talk. And so I'm pretty sure that you are here for the nice science, but please let me spend about 2 minutes to introduce Dr. Zhao. And he graduated from USTB in China in 2010, and he went to Germany first. Intend to start his PhD, but unfortunately he's widely retired after about 3 years, as I see in his website. And then he moved to UC San Diego and worked with Professor Meyer to start a new PhD, and he got graduated from UC San Diego. After that, he moved to Lawrence Berkeley National Lab and worked with Professor Andy Miner. And then he kind of transferred from laser to microscopy, from my understanding. Please correct me if that is not true. And then he made a lot of impactful work during his PhD and also his postdoc. So to give some examples, he published about, I think it's 4 papers, like one in Nature Materials, and 2 Science Advance in just 1 year. I think it's last year, because I'm a fan of his research. So I sort of follow his Google Scholar last year. So that's really, like impressive in the field of material science, especially in the field of metallurgy. So that's also one of the reasons I'm so pleased that I can host his talk today. So I'm pretty sure some of you guys are also, curious about his science and want to learn from his talk. So without too many wasting of your time, so I will return this time back to Dr. Zhao. Now it's your turn. You can start your talk.
Thank you, Dr. Ouyang. I guess you can quit share. I can share my screen. Yeah. All right. Can you guys see my screen okay?
Yeah, I can see it.
Yeah.
All right. Thank you. Thank you for the nice introduction, kind introduction. And thank you for this wonderful opportunity to present my work in this awesome platform. Again, my name is Shiteng Zhao, Zhao Shiteng. I recently joined the Department of Material Science and Engineering, Beihang University in China. Well, actually last month. So this is my very first webinar ever since I joined the department. Before I get into my research seminar, I'd like to say a few words about the TMS to show my gratitude. Well, actually, the first time I heard of TMS, I was laughing because I guess for many of you who conduct research in metal community, we also have a TMS society, but which stands for different things, right? It's actually called the Material, Mineral, and Metal Society. We often call it the Triple M Society. So I thought in the beginning, somebody must be joking on this very old traditional TMS society. But when Haocheng and Dr. Ying was introducing me the core concept of this TMS, the new TMS, shall I say, I immediately was shocked, and I think this is a fantastic thing to do. It's a noble thing to do because it actually one of the goals is to promote young scholars, to give them the opportunity to make their voice heard. And I think this is extremely important in this world in academia, and we're facing so many injustices and so on and so forth. So I only wish the TMS Society all the best in the future, and I look forward to the TMS growing into sort of a flagship for the scientific seminar internationally, and also I have no doubt that the TMS will be a harbor for young scholars internationally. Okay, so going back to my research topic, so today I'd like to share with you some of my work over the years. Like I said, I just joined the department, so most of the work I'm showing today was done either at Berkeley during my postdoc training or at UC San Diego during my PhD. So a little bit of background, I guess one of the fundamental challenges we're facing today is that the service condition of materials ever harsher, more extreme, and start to deviate from the so-called equilibrium conditions. For example, in the aerospace engineering industry, we are allowing for better high temperature materials like superalloys, which can sustain higher temperatures. Another example is plasma phasing material in fusion reactor, right? It actually challenges the current alloy design because the material has to face, very high temperature and also corrosive environment. And in China recently have committed, to realize carbon neutralization by 2060. So I guess that requires collective efforts from all the industries. One of the industry, like automobile industry, they have to find better structural materials, more lightweight, to improve the energy efficiency. So in a word, I guess the takeaway here is we need better materials. We need better alloys. So when we talk about alloy design, right, the traditional way of doing so is to look at the phase diagram. So here is a very typical iron carbon binary system, which is already pretty complicated. It actually maps out what type of phase will shows up at different temperature and different chemical composition. But unfortunately, this is just part of the story, okay? Because this is equilibrium phase diagram. It only describes the materials under equilibrium conditions. If the thermodynamic state of variable is changing as a function of time, this phase diagram will become less and less valid. This is intrinsically because the energy landscape of materials is not that simple. It's not you have low energy states, which is equilibrium states, but you also have lots of local energy minimum, which correspond to different non-equilibrium phases or metastable phases. So this poses significant challenges on our understanding of materials, but at the same time, it also provides opportunities because all these non-equilibrium phases, they may be just beneficial. They may have better properties. So to me, this is another dimension of alloy design or material design. But the fundamental question remains, what is the path dependency of this microstructure property relationship? So this is the fundamental science question, I'm asking upfront. So today, I'll use 3 examples to demonstrate what I mean by non-equilibrium deformation and engineering. I don't think I have enough time to go through all of them. Hopefully I can go through first 2. So the first one concerns with deformation and failure mechanisms of material at extremely high strain rates. So what is strain rate? A strain rate is a parameter that defines how fast we deform the material. Normally, when we talk about deformation, we refer to deformation as in quasi-static condition, where all the atoms in the deformed body sort of feel the load simultaneously. But this assumption becomes less and less valid if we increase the strain rate, because at that time, we start to create a stress wave. A stress wave is a acoustic wave that travels with sound speed. Now, if we hit the material hard enough and fast enough, we may create a supersonic states, which corresponding to a shock wave that typically at a strain rate about 10 to the power 6 per second. And of course, this corresponds to extremely non-equilibrium states, and usually it is associated with extremely high temperature, pressure, and of course, everything happens within extremely short period of time. And this is very normal in our universe, right? From supernova to interplanetary collision, and also hypervelocity impacts. For example, when our space exploration device it will be threatened by all the space debris, which is flying around the orbit with an extremely high speed. So scientifically, well, this raises fundamental questions as to how condensed matter or materials react to these extreme states. And turns out that our understanding is quite limited. Even in a very, very familiar material, for example, water or ice, our understanding of this material in the non-equilibrium states is still far away from fully understanding of these materials. So this example shows here a Nature paper back in 2019. A group of Leibniz scientists discovered a very exotic state of ice called superionic ice when they subject the solid state ice to extremely high pressure and temperature using laser. So this is the first time that we actually synthesize this very peculiar phase of ice. So indeed, time scale matters, right? And again, our understanding of materials in these conditions is still very limited. And for example, to our material scientists, right, we don't understand the deformation mechanism in these extremes. And there are just so many metastable structures and phases waiting to be explored. So to tackle these challenges, right, we should either develop a new technique that can subject materials to these extreme conditions, or we need to develop new characterization technique to look at these materials better. So talking about shock, I mean, there are many different ways to conduct a shock experiment, right? Here I just show you a relatively new one called pulse laser-driven shock experiment. So firstly, a high-power pulse laser. Let me bring the laser pointer. Oops. I see. Okay. So when you shine a piece of intensive laser onto a target, it will ablate the front surface into plasma, which leads to a rapid volume expansion, which drives a shockwave that propagate into the materials. And this process is called laser ablation. And the pressure generated by this process scales with one, the laser intensity, two, the wavelengths of the laser. So now you can do two types of experiment. The first one is called shock recovery, where you can recover the material shocked from high pressure and start to look at microstructure in different scales. And secondly, you can conduct in situ experiments by a technique called VISOR, velocity interferometer system for any reflector. It basically can measure the velocity of the shock target as a function of time. And by applying an equation of states, you can back calculate the pressure profile as a function of time. So the figure on the upper right corner is sort of a device that we designed and implemented at Lawrence Livermore National Lab. It allows us to shock recover some very brittle materials, which traditional method cannot recover. And also you can do preheating and also multi-field coupling shock experiments. Well, the takeaway here is using this technique, you can generate extremely non-equilibrium states, high pressure in the megabar region. 1 megabar is 100 gigapascal within nanoseconds. So everything happens in extremely short period of time. So using this technique, we actually studied a variety of materials. And here I plot the so-called shear stress and function pressure in this 5 materials we studied. So shock is actually a very complicated phenomenon, but to simplify shock, you can try to model it in solid mechanics as in uniaxial strain, which can be decoupled into a hydrostatic compression as well as a strong shear component. And the shear stress is responsible for many interesting phenomena. For example, plasticity, stress-induced phase transition, and some even more interesting and peculiar phenomenon that I'm going to talk about in just a second. So when we talk about shear stress, right, the material has to relax the shear stress above certain threshold, and normally this is realized by plasticity, where you can generate a high density of defects and motion of the defects. And sometimes you can use mechanical twinning, and sometimes you can use a phase transition to relax the shear stress. All these mechanisms are a classical picture of plasticity, and is summarized in this diagram. But when the time scale involved in the deformation is significantly reduced, you basically force the material to undergo some new interesting phenomenon. And in the laser shock of these 5 particular materials, we observe something called shock-induced amorphization of the materials. So basically, we observed beyond certain threshold, a shock pressure threshold, the material undergo a very drastic phase transition from crystalline to a disordered amorphous structure. And if you look at the high resolution TEM images of all these materials, the amorphous region shows a shear band-alike feature, which indicate again that shear stress play a significant role in this process. So, so this is something that has been reported before in other shock experiment. By using laser, we can subject the material, can reserve the material in one piece, because the short time scale involved in the laser experiment largely suppress the propagation of cracks. So, for example, if you think about silicon, it's extremely brittle. Right? You drop a piece of silicon wafer onto the ground, it's just shattered in pieces. But if you hit the silicon with a piece of nanosecond laser, although you generate a transient pressure, which is much higher than the load that the wafer dropping onto the ground, but you still reserve the material in one piece. So that's the significant advantage of nanosecond laser to study the deformation mechanisms of these brittle materials. So we of course want to understand the mechanism of amorphization, and I don't want to get into the details, but essentially we try to understand whether this amorphization is achieved through melting and quenching, or is it solid state, right? So here I just plot this in these 5 different materials we study, the phase diagram against the shock-induced temperature rise. The solid line is basically the phase diagram. The dotted line is the computed temperature rise at the shock front. So as you can imagine, the intersection between the dotted line and the solid line gives you the so-called thermodynamic melting point. And the reason to do so is that experimentally we can measure a threshold of amorphization, and using this we can compute a thermodynamic melting point, right? And it turns out that the computed melting point is always larger than our measured amorphization threshold. So this indicates that the amorphization is not melting, right? It's still in the solid state. So if amorphization is solid state, right, but amorphous phase is energetically less favorable, then what is helping such a phase transition? So one thing we notice from high resolution TM is that amorphization always occurs in the vicinity of a high density of defects. So we performed lots of high resolution TM observation and also conducted MD simulation. Well, I don't think the video works for some reason, but the idea is we try to simulate the process and confirm that amorphization occurs through either the propagation of stacking faults, in this particular case is silicon, or amorphization occurs at the intersection of all these high density of planar defects. And based on this, we kind of proposed a modified thermodynamic framework taking into account that shock generated defects. Basically, it's a two-step process. We assume shock firstly produce a high density of defects, and then the amorphous material starts to nucleate in those highly defective area. And this is this simple model captures our observation. So we observed the shock-induced amorphization in a variety of material. Then the question is this a universal mechanism, or is this material specific? So our hypothesis is that amorphization would occur in a material whose dislocations are hard to move, or in other words, the Pyre stress or the value to move a dislocation is close to its theoretical strength. So if we plot the normalized Pyre-Navarro stress against the dislocation line energy of the materials, we see here that the material we saw that can undergo amorphization pretty much lies in the upper region. Again, this means that the traditional mechanism is hard to operate in these materials. So therefore, we propose that this directional amorphization can be a general deformation mechanism when the materials are subjected to extreme loading conditions. This extreme loading condition can either be high stress state, high strain rate, or high strain energy, input energy. So of course, there are still many remaining questions, for example, how fast amorphization would occur and how it can accommodate the plasticity in polycrystalline materials. So these questions are pending further investigation. Well, actually, just a couple months ago, several groups, actually including our group, discovered directional amorphization in a metallic system, which is not included in this paragraph, and this indicate that this amorphization is even more general. Okay. So speaking of the metallic system and high entropy alloy, right, which is pretty hard topic right now in the physical metallurgy community. Well, the reason we are interested in high entropy alloy is that, well, for those of you who don't know or are not familiar with high entropy alloy, it is basically a material that has multiple principal elements with almost equal atomic ratio. And previously, people have demonstrated that some material system can actually have excellent cryogenic mechanical property, and which is attributed to twinning induced plasticity. And this is a good news for us who study high strain rate phenomenon, because in metal forming community, if you look at this so-called Zener-Holman parameter Z, high strain rates, which is in pre-exponential factor, and temperature, which is in the denominator within the exponent, high temperature and high strain rate and low temperature, they have similar effect. So this means if the material has excellent cryogenic mechanical property, oftentimes it is very good at high strain rate. So this is our motivation. So we chose a particular system, chromium, cobalt, nickel, very classical, so-called media entropy alloy. And we use the same methodology, right, to shock recover this material in a peak pressure about 15 gigapascal. As you can see from this low resolution STEM image, there's a high density of defects generated by shock. And, these defects having this type of a planar feature. And if you go to higher resolution, you can resolve the atomic image of this deformation features. Sometimes it's a stacking fault, sometimes stacking fault intersection, leading to a so-called Lumer culture lock. Sometimes you have a nanotwin, and sometimes you have HCP lamella. So this means the material has undergo FCC to HCP phase transition, which is similar to the trip effect or in some high manganese steels. But this is everything happens on the compression, right? If we want to evaluate if the material can be used at high strain rate, so compression is not good enough. We want to subject the material to dynamic tensile stress state. So that's why we are looking at a dynamic tensile. Well, the reason to do so is because most metals failed in these conditions by a tensile load. Again, I don't think the video worked, but somewhere I have a video here. So if you look at the video, I mean, the shock front is here, right? It's compressed the material along the way and generated lots of defects. And when the compressive wave reaches the back surface, which is the free surface, the stress line will be flipped into a tensile wave. And tensile wave is destructive. Ultimately, it leads to void nucleation, and the void will grow and eventually coalescence. And so this is the dominating mechanism of ductile failure in materials under dynamic tensile loading condition. So, you know, this is a very good demonstration of how metal fail, and actually in reality, this is exactly how how metals failed. So this is a photo taken by European Space Agency where a piece of metal has been hit by a space debris. It has a scary crater on one hand, but that's not the most destructive thing, because there's the internal fracture on the back surface, right? The mechanism is something I just described. Is because, you know, the compressive wave has been reflected back as tensile wave, and the tensile wave just pull the material apart. So this is a dominating failure mechanism at hypervelocity impact, for example. And in using laser experiment, we can actually mimic this extreme deformation and failure, of course, in a much smaller scale, but we can quantify this process by measuring the so-called Spall strength of the material. You know, Spall strength is something you can imagine the ultimate tensile strength in quasi-static condition. Basically, you can think of that as a fracture strength of material in a dynamic loading condition. So since we have the way to measure the Spall strength of material, we can evaluate whether this high entropy alloy is good or not at high strain rate tensile loading, right? So we measured the Spall strength of, again, this chromium cobalt nickel medium entropy alloy. And here is the recovered sample, right? This is the front surface. You know, this is the back surface, which has a bubble, which indicate that material has developed some internal cavity. Basically, the material has been pulled apart. So we measured, again, the Spall strength of the material. Before that, we measured the sound velocity, the longitudinal, the transverse sound speed of this material, and evaluate the strain rate, which is in the range of 10 to the power 6 to 10 to the power 7 per second. So the measured Spall strength is around 10 gigapascal, which is actually decent. If you compare this with other metals, for example, tungsten, 8 gigapascal, aluminum 3, iron 5, copper 8. So the high entropy alloy is pretty good. It's pretty good. Although compared with its high cost, you know, it's hard to, it's a hard sell for the actual application, but scientifically, there's lots of things, interesting things to be investigated. So I want to switch gear a little bit to a second topic, if I have time, which is concerned with electroplasticity. So electroplasticity is a very traditional phenomenon that was discovered in late 1950s, when people realized that, you know, the application of high density direct current leads to a reduced flow stress as well as enhanced ductility. This is good for metal forming, right? Because compared with other metal forming technique like hot rolling, it is economically favorable. You know, this is basically an example of aluminum alloy where there's a very brittle secondary phase. And by applying a current, every time we apply a current, you know, the flow stress reduce, and looks like the tensile ductility increase a little bit, okay? This is the typical observation for electroplasticity. But traditionally, in terms of mechanism, it's very difficult to understand what's going on. Initially, people just believe, you know, electroplasticity is nothing but Joule heating. because every time you apply a pulse, you heat up the sample, and thermal softening will give you similar effect, right? But I guess there's enough literature suggests that there's something else going on. For example, people propose that the electrical pulse may influence the so-called thermal activation of dislocations. And another more classical proposal is so-called electron wind force, which is a concept borrowed from electromigration. It's concerned with the direct momentum transfer from the drifting electrons to dislocation, which exert a pushing force on dislocation, make the motion of dislocation easier. And there are other proposals like magnetic restriction, pinch effect, and free energy minimization, so on and so forth. These proposals are all, sounds very reasonable, but it's difficult to decouple from each other and more importantly, from Joule heating. So when we look at the electroplasticity, we are trying to understand it from a pure material perspective. Can we find a material that helps us to decouple all these mechanisms? So we chose a material system called titanium aluminum with 7 atomic percent aluminum as a model material. The reason is the following, right? At ambient temperature, aluminum can dissolve in titanium matrix to form a disordered solid solution up to 10%, above which the material start to precipitate the DO19 titanium-3 aluminum intermetallic compound. However, even within the solubility limits, if you heat up the sample at intermediate temperature, aluminum tends to undergo something called short-range ordering, leading to the formation of a short-range, usually within a couple of nearest labor, DO19 alike domains. So this is a well-known phenomenon which has been documented in the literatures. The consequence of the short-range order on plastic deformation is that it leads to a planar dislocation slip, right? Which potentially is the cause of shear localization and therefore the early fracture of the materials. Therefore, as you can imagine, the ductility of this material is not going to improve if you increase the temperature at intermediate temperature, because at this temperature, the high temperature basically promotes short-range order and promotes planar slip, right? Now the logic is, if you apply electrical pulse, if you increase the tensile ductility, that can at least tells us, thermal softening is not the cause. There's something else going on. So we performed a series of tensile tests under different conditions, right? Pulsing here means tensile test with electrical pulse arm. And we indeed observed that by applying a pulse during tensile testing, we indeed improve the tensile ductility. And this is a macroscopic observation. But at microspace, we always try to find microstructure mechanism. And so we indeed look at the microstructure by TM at different stage of plastic deformation. And here on the right-hand side, there's 2 columns of TM images. On the left-hand side is basically the reference, the room temperature deformation without any electrical pulsing. On the right-hand side is basically tensile test while you apply electrical pulse. And we observe a sharp transition from the reference state where we observe this really regular 2-dimensional planar dislocation slip to a 3-dimensional wavy dislocation slip if you apply electrical pulse. So then we conclude that the electroplasticity should in principle originate from defect level reconfiguration in this particular materials. And here I show you perhaps oversimplified picture as to why a wavy dislocation is preferred over planar slip, right? From the left-hand side, the planar dislocation slip configuration, this, like I said before, it leads to a localized shear displacement on a particular slip plane. If the dislocation of a screw type, right, the resultant strain field is similar to a type 3 shear crack. And therefore it might lead to stress concentration and provide a nucleation site for early fracture. In a sharp contrast, right, a wavy dislocated slip means that the dislocation distribution all over the place, leading to a homogeneous partition of the plastic strain, which can sustain the work hardening of the materials. And therefore, the ductility of the material will be better if you have a wavy dislocation slip. Now, why electrical pulse can trigger this planar to wavy slip transition? So if you think about how the planar slip is developed, right? If you have a short-range order on a particular slip plane, the passage of a couple of dislocation will destroy that short-range order domain. And as a result, it will basically lower the critical resolve, the required resolved shear stress to activate dislocation on that particular slip plane. And therefore, the following dislocation will tend to get onto that plane. This is called slip plane softening, and it eventually leads to a two-dimensional planar slip. Now, if you supply electrical pulse, our hypothesis is that the pulsing somehow trigger or promote cross slip when the dislocation is temporarily arrested by the short-range order clusters. And this results in getting out of the original planar slip plane, and as a result, it becomes a wavy three-dimensional distribution of dislocations. So again, it is our hypothesis, right? We don't have a direct evidence of a cross slip, but my colleague at Berkeley right now is doing in situ TM while applying electrical pulse. Hopefully, we can provide some direct evidence of cross slip in the near future. This is pretty much my talk. I don't want to read my summaries, but I'll just get into the acknowledgement. You know, I'm fortunate to work with many people, good people over the years, starting from my PhD at UC San Diego. It's very diverse and vibrating group, and we collaborate with people from, for example, Caltech, from Army Research Lab, and also the electroplasticity work was done at UC Berkeley. We are also very collaborative people with folks from computational side, experimental sides, in very pleasant working environment. And also the folks from Livermore provide us the opportunity to use their laser facility, which make our amorphization work possible. And you know, this type of experiment is extremely difficult to perform, and I thank them for their very professional help. And of course, there are many people many of my colleagues now has become professors here there. You know, Shear and Zhao University, and also folks from University de Cuyo in Argentina, Carlos and Eduardo, and also folks from Oxford University. And also, of course, you know, I thank all these funding agencies for support my work. And although I'm no longer eligible to apply for any of this funding, well, I thank them for their past support. So with this, I'd like to conclude my talk by saying thank you, everybody, for tuning in today. And I'd like to answer any questions if you have them. Thank you very much.
I had a question on the medium entropy alloy. So we sort of know that high entropy alloy or medium entropy alloy are kind of closer to amorphous because they have larger distortions, and usually in XRD they have broadened peaks. But on the other hand, people argue that there are sluggish kinetics in these materials.
Right.
So this sort of this sort of brings up a contradictory situation about the amorphization, because when you make amorphous metal alloys, you want high diffusivity, right? Also demonstrated by the nice story of ice. But high entropy doesn't have it. But the structure itself is close to amorphous. So could you comment a little bit on whether when you shed a laser on high entropy alloy, would the amorphization be like faster than typical alloys or slower than typical alloys? And I mean, it will be nice if you have explanation for that.
Yeah, thank you, Ouyang, for this. I think it's a brilliant question. Well, you mentioned that high entropy alloy is similar to, for example, bulk metallic glass, right? In the sense that, first of all, it has, in both materials, there are multiple principal alloy elements, and secondly, large distortion, and so on and so forth. But this can be reflected by the community of high entropy alloy migrated from the bulk metallic glass community. Most people who do high entropy alloys are actually those people who studied metallic glass for a very long time. Now, going back to the similarities between high entropy alloy and amorphous, I mean, I don't think it's, well, I don't see direct similarities because, first of all, it's although there's a huge lattice distortion in some high entropy alloys, that does not mean that all the high entropy alloys have large lattice distortion. For example, in the example I show here, the cobalt, chromium, nickel, right? I mean, the three transition metals, if you look at their atomic radii, very similar. So if you look at the X-ray direction, you don't see the peak broadening. So it's, in a sense, it's still very similar to pure metals. So the transformation from a high entropy alloy or crystalline to amorphous by mechanical loading, I still think it's pure mechanical. The mechanism, as I mentioned, there are still some remaining questions, but the argument is if you can pump enough defects into your system, you can potentially increase, the free energy of the crystalline materials to an extent where the crystalline structure will no longer be energetically favorable, and that can trigger amorphization. And again, everything will happen within solid state. So the criteria to amorphize this type of material is no longer the criteria to produce bulk metallic glass, where, for example, you heat it up, you melt it, and then rapid quenching, right? I mean, theoretically, you can produce glassy states of everything if you have fast enough quenching rate, but practically some material is preferred. But there are many criteria proposed over the years. You may be more familiar with that than I do. But solid state amorphization, in my opinion, is still mechanical effects. The idea is very similar to ball milling, right? Because in ball milling, where you have lots of metal powders, and if you throw them in a ball miller and give enough time, the powder will plastic deform and accumulate enough defects, and that triggers amorphization too. In our case, we're just using high strain rate at the demonstration, that this can also happen. And so that's why in that figure, we propose that amorphization is a phenomenon that potentially occur in extreme condition. This extreme can be defined as extreme high stress state, extremely high strain rate, or perhaps a more rigorous definition is more extreme input strain energy. So yeah, I don't know if I answer your question, but this is my current understanding.
Yeah, thanks for the answer. It's very comprehensive. So may I understand that it's kind of depending on the defect tolerance of the material rather than something else? That's what you define as mechanical reason, right?
I'm sorry, say it again.
So my understanding from your explanation is kind of like it's depending on the defect tolerance of these materials. So in that case,
right.
if
Exactly,
it can generate more defect, then amorphization gonna be enhanced in that way.
Right. So the idea is right. I mean, in the beginning, when I was demonstrating amorphization, all the examples are brittle materials. The idea is in brittle materials it's very difficult to pump a high density of defects by traditional method because they're just brittle. If you want to plastically deform it, it just tends to shatter into pieces. But using high strain rate nanosecond pulse laser, the high stress state will decay to a stress that crack can no longer propagating. So by doing that, we can somehow suppress cracking and force the material to undergo plastic deformation. And of course, we have other tricks. For example, confine the material in a ductile cylinder when we do the laser experiment. But the idea is if you can suppress cracking, and the energy has to be dissipated in one way or another, either cracking or plasticity. So in brittle materials, we achieve this by nanosecond pulse laser shock compression. But in ductile metals, we have to think about other factors because ductile metal have just so many ways to dissipate strain energy, right? Dislocations, twinning, monocytic transformation. But the key is to pump as many defects as possible. We have to find a material system that is suitable for doing this. One simple, perhaps oversimplified criteria is to find a material that has the lower stacking fold energy. Because by choosing a low stacking fold metals, you basically suppress recovery, which means the defect density during plastic deformation will, keep going without reducing, something we call recovery in plastic deformation. So low stacking fold energy materials recovery is suppressed, and therefore you can keep pumping defects. So that helps, in my opinion.
I see.
Yeah.
Thanks a lot for the answer. So there is actually a waiting queue here. So I would like to give this opportunity to other person. Like, Haocheng, do you want to organize, or I can go ahead?
Dr. Shiteng, you can open your unmute yourself and just ask a Shiteng question.
Yeah, excellent talk, Sudha, as usual. So I learned a lot from your talk every time. So I just have a quick question and also want your comment about the short wave propagations in the materials. So as we all know from, for example, linear elastic wave, the wave propagation actually is highly affected by the boundary conditions. Right. And also we have the saying called wave guide. Basically, we use those boundary conditions and also the coupling between shear wave and P wave, S wave to guide the wave propagation. And right. I saw in your talk, for most of the short cases, the short wave mostly is understood as a 1D short wave propagating. So I just want to hear your comment about, like, is there any boundary effect that also can help us to guide the short wave propagations, or is it like or it just doesn't matter? I mean, in most cases, just like just a 1D is good enough for describing the short wave. Yeah. So can I ask the second question so that you can answer together? Okay. And the second part of the question actually is about the amorphizations process when the short wave pass through the materials. So so is it the amorphization just like the results or the damage generated by the wave? It's like so once you have wave propagate, just creating a lot of stuff and then generating amorphization, or it's like it's a coupling to the short wave. It's like once you have that amorphization, it also change or tune the short wave propagation. So which one you think is a little bit closer to your experimental result, or neither of them are true based on your observation? So this is my two questions.
Good questions, Shiteng. Well, to your first question, I think, of course, the boundary condition always matters. It's just, you know, in our experiment, we tend to simplify things by assuming, you know, this is one-dimensional. Well, in reality, you always have confinement of, because we try to defocus laser spot to be bigger than the simple size, so that you don't have edge effects, right? You know, the boundary condition comes in when the wave reaches the boundary, and then you have reflection and you know, all kinds of complicated interaction. So we try to you know, have a planar shock wave without taking into account of the boundary condition. But you're right, you know, boundary always matter, right? We actually saw this, you know, when you shock using laser to shock a huge piece of metal, so only you have a small piece of metal has been shocked. If you do a cross section and do a BSD and compute the geometrically necessary dislocation, you would assume, if you don't have boundary condition, right? You would assume, you know, the planar wave traveling from upper traveled vertically. But if you compute the distribution of J and D, or in other words, the distribution of plastic strain, it's not like that. It's not that simple, right? I mean, it has a cone shape. That means, you know, the wave has reached to the edge of the sample, reflected back, and so on and so forth. So it is, the boundary condition does matter. Well, actually, in shock community, people have been using something called shock tube. You can focus two shock, you know, at one point to double the magnitude of the shock wave. And so this is some sort of this can find some application in weaponry development and so on and so forth. But, you know, in our study, we try to simplify things, you know, by assuming it's a one-dimensional planar wave propagation. Now, to your second question, whether wave propagation being affected by amorphization or vice versa is sort of a chicken and egg type of question. I mean, I would assume, you know, if you have a shock wave propagate through the material, you know, it will amorphize things behind the shock front. Well, I don't know, because I don't have in situ, and frankly, I don't think the in situ diagnostic today can resolve that fine structure. But let's assume if amorphization occurs right after the shock front propagates through the materials, so that doesn't affect shock propagation, right? But when the shock wave reaches the back surface and then reaches back, of course, it will affect, you know, the propagation of the stress wave, because, you know, amorphous material is isotropic and crystalline material is anisotropic, and the wave propagation in these two complicated different materials are, of course, different. But again, this is, in my opinion, it's too complicated to solve analytically. But, you know, I mean, maybe if you're interested, you can, a smart one like you can tackle this problem.
Yeah, thanks. Yeah.
Thank you.
Thank you, Shiteng. Thank you for your answers. So, Fei Zhao?
Hey.
Yeah,
Can
so
you hear me?
please unmute. Yeah, we can hear you. So just ask your question.
Okay, I have two questions. So I focus on the orthostatic pressure, but hydrostatic pressure. We found in Cantalloy you know, we find the FCC to XCP, but in hydrostatic pressure, we didn't observe the amorphization. So do you think in synchrotron radiation, maybe pulsed X-ray, we can in situ observe the shock-induced amorphization? So,
yeah, I think I met you somewhere, right, in TMS. Are you from? Are you in Shanghai, right?
No, I'm in Beijing. I'm have to construct the high energy photon source.
I see.
In Huairou.
Okay.
Yeah.
Okay.
Okay.
Fair. Yeah. So the question is a good one, and I look forward to the capability of a synchrotron facility in the future. I mean, my understanding is someone is building a beamline, either in Shanghai or Huairou, to couple a synchrotron with, you know, laser shock or whatever. It's similar to the LCIS at Stanford, right? So this type of experiment, in my opinion, is the future of high strain rate community, and I really look forward to you know, using it, perhaps collaborate with you in the future on this topic. But back to your question, can synchrotron resolve this fine structure? Maybe, maybe not, because to probe this really fine and subtle phase transition, you really need high spatial resolution.
Yeah, one question is the amorphous phase, the volume fraction.
Right.
So,
yeah. So that's, yeah. I mean, if you have a high volume fraction of amorphous materials, for example, in the case of covalent bonded materials, for example, silicon, the volume fraction at shock front of amorphous materials is pretty high. I don't have a number in my mind, but I would assume it's, you know, 10%, something like that. So you should be able to probe that by synchrotron. But in the case of high-entropy alloy, I think you mentioned you did some work of a static high pressure in DAC, right? Diamond Eversole, right?
yeah.
In that case, you know, the volume fraction of amorphous material may be higher because the shock is a transient loading process. The peak pressure will decay within, depending on the duration of your technique of your laser, for example. You know, so the volume fraction of high-entropy alloy produced by laser shock will be pretty small, if any. But that does not mean it's not possible, because, as I said, the capability of high-entropy alloy to undergo this stress-induced amorphization depends a lot on the chemistry. If you tune the chemistry of high-entropy alloy in a direction that favors amorphization, and therefore you generate a higher volume fraction of amorphous material, there might be possibility that, you know, you can study this in a synchrotron facility. And I look forward to that, because only in a synchrotron facility can you actually prove everything in situ. You can actually compare your results with, for example, MD simulation. So in my opinion, that's the future of this type of study. So unfortunately, I don't have a clear answer to your question. It's all possibility. I mean, I'm optimistic. That's my short answer to your question.
Okay. Actually, I'm a postdoc on the high pressure beamline in Beijing now. So we have some hydrostatic facility, you know, DSA. Actually, we also have dynamic DSA. We can pressure the sample 1 second, maybe several hundred dPa. but the X-ray time structure is not enough for the to get enough diffraction signal. So
I see.
So maybe we can discuss later.
Yeah,
we
sure,
would like
sure.
to.
You have my.
Yeah.
Are you where did you do PhD?
USPB.
Right. I remember you. Are you students of Professor?
Zhao.
Yeah, I remember.
Yeah.
I think I have your WeChat still.
Yeah, we have. Okay.
For sure.
Okay. We can discuss later.
Thank you.
Thank you. Okay.
All right, thank you for your answer. And so, Julian, you probably can unmute yourself and ask your question.
I think I can ask one question. Like,
okay, James, go ahead.
Yeah. So just I'm kind of very interested in the shock-induced directional amorphization. So I'm just curious, like when you do the laser shock deformation to introduce those amorphizations, like I'm just wondering what's the size and dimensions of the samples you are using. So I just want to see if any potentials in using this this kind of technique to make some new structures and new materials. Yeah.
Yeah. Right. I think what you are really trying to ask is so what, right?
No, not so what. I mean just like the potential of, because it's kind of similar to what I did to the glass before. It's just using laser to introduce some this kind of structure or material. Kind of, you can call it the defects, but it can be make some interesting structures like that.
Right.
So that's I want to see the potential of those. Yeah.
Well, the laser we are using, they are all very powerful, gigantic laser. It's not commercial laser per se.
Yeah.
But it doesn't mean that it cannot be used. Well, there in industry, there's already a very useful technique called laser shock peening, which is used widely in aerospace engineering, where people use that to produce a compressive residual stress on, for example, aerospace engine to enhance the fatigue life of the materials. In our case, right, it is more of a surface modification, right? I mean, you produce a peculiar structure, a different structure compared with your matrix, so, I mean, we have done a series of experiments on silicon, right? And we indeed see, for example, when you tune the parameter of laser and therefore the pressure profile, you can have a different structure, from for example, a different phase of silicon to amorphous, and then amorphous structure can recrystallize into non-crystalline materials. So indeed, this can be a very expensive way of prototyping nanostructured semiconducting materials. Well, it's very, very expensive, I should say. But so yeah, I mean, this is more fundamental research, and hopefully, well, if the laser can be, for example, commercialized with more acceptable price, you can do something more practical.
Okay.
Yeah.
So another follow-up question is like, except for in addition to use laser, is there any other ways to kind of like other methods to actually make those shock introduced amorphizations? Like, I don't know, like probably like supersonic would be the energy would be too low, but would there be some other ways other than lasers?
Yeah, well, as long as you can produce shockwave, in principle,
Okay.
And of course, you have to try to think about a way to recover the materials.
Yeah.
For example, back in 2003, a group of people from Johns Hopkins, they actually recovered some powder of boron carbide from actually a military when they recovered the powder from penetration test, where they use they fire a bullet using for example a pistol, whatever. They fire bullets towards a boron carbide armor, and the armor shattered into pieces. And they grab a piece of powder and look at under TM. They saw amorphization, and that's the first time they saw amorphization in boron carbide. The advantage of laser is that, again, like I said in the seminar, in the webinar, it is, in my opinion, it's a cleaner experiment because you still preserve the sample surface, and the loading direction. You know the loading direction with respect to your amorphization direction, and so you can conduct some mechanical analysis in contrast to just recover some powder from a mass. Okay. Yeah, so of course you can use other technique to produce amorphous structure, and I think we have done other ideas. I'll talk about that in my next TMS talk.
Okay. Yeah. Thank you so much.
Already try to make a reservation for next series. And hi Chu. So are you back?
Hello, can you hear me?
Yeah, we can hear you. So please.
Oh, okay. I'm sorry. Yeah. So thank you very much for your nice talk, Dr. Zhao. My name is Haocheng from Nanjing University of Aeronautics and Astronautics, and I just come back to China 2 months before. So before I was working in the University of Tokyo, and actually I was working on the plasticity by using direct current. So okay. you use pulse current, right?
Right. You use pulse current, exactly.
Yeah. So I'm quite interested in your topic on this part. So you found that so maybe that is your assumption that the cross slip can be promoted by the pulse current.
Right.
Yeah. So how do you think the effects on other material, because you choose the material is kind of special.
Right. Yeah, I think that's a fair question, right? Like I said in the presentation, the reason we choose this material is try to decouple the pulse effect, the current effect from Joule heating. We kind of achieved by using a special material system. But I think the assumption still holds in a sense that the electroplasticity must come from defect level. The current assumption is pulsing may trigger cross-slip. And this mechanism can be universal, right? If it's true. I mean,
yeah.
I mean, we don't know yet. My colleague in Berkeley is trying to do some in situ TM to verify this hypothesis. But I think she has other proposal. She has other mechanism proposed. So the cross-slip may not be the only explanation. I mean, I don't know the particular material system you study, but in our material system, because there's a sharp transition between planar to wavy dislocation, that sort of make the observation clear. But if you have a material that already have a wavy sleeve to begin with, then the pulsing effect would be very difficult to observe by this post-mortem type of analysis. And if you are working on electroplasticity, you must be familiar with all these literatures. And I'm sure you know, there are basically all kinds of proposals, right? The pulsing may affect the thermal activation of dislocations, right? Either reduce the energy barrier of dislocations, or it actually you know, affect the so-called tamping frequency of dislocation. That's actually buried in the prefactor of that equation. And there are other proposals. For example, if you apply a pulse current, right? You know, it also has to do with how fast your pulse. I mean, I'm not talking about the duration of the pulse. I'm talking about how fast the current goes from 0 to your peak value, and that's.
So you mean the speed, the response?
Yeah, yeah. Because that has to that short period of time has to do with, for example, the vibrational frequency of dislocation, which is very important. For example, in core sleep. But all these mechanisms and proposals are hard to justify because there's no measurable, at least for now. It's difficult to measure. It's difficult to measure. That's my.
Yeah. Thank you. And because you use pulse current, so how do you think the electroplasticity also exists by using the direct current?
I'm sorry, say it again.
So now you use pulse current, right? Pulse current has the duration time and the many parameter. But I was using direct current DC. You use PC. Yeah, I was using DC. So how do you think the electroplasticity also existed by using the direct current?
We use DC too.
You also use DC? Yeah,
we use DC. It's just a pulse DC. Not, well, AC means, you know, the direction of current flipped, right?
Yeah.
You know, this is something, if you look at the literature, most of the literatures are talking about DC. I barely see AC current used in electroplasticity. You know, the reason is, you know, if you use AC, right, there's a skin effect. The current will localize in the, it's not going to be homogeneously distributed across your sample. And I mean, it's already complicated.
Okay. So you use DC, but you change the pulse parameter that which be applied in experiment.
Yeah.
But so what about you don't change the duration time? For example, you just keep current.
Yeah, that's a good question, right? You think so you don't change the duration of the pulse, but change the amplitude of the current. Is that?
Yeah.
Well, I would argue. Yeah, I would assume that. I mean, by raising the amplitude of the current, you of course also increase the temperature, right? The heat generated during electroplasticity, right? I mean, if you think about all these mechanisms, right? The wind force scales with current, or scale with number of electrons. So in principle, it should scale linearly with the current density. But if you couple that with heat, you know, I guess everything will become nonlinear. I mean, of course, I think by changing the amplitude of current will affect the mechanism, well, not mechanism, but change the effect of electroplasticity. But the direction, you know, will it make it better or worse? I don't know. I'm not so sure yet.
Okay.
But you know, this is basically you have to perform in a. I mean, there's a huge parameter space, right? There's pulse duration, there's a pulse amplitude, and also the shape of the pulse. So in order to study this systematically, you have to perform lots of experiments, you know, but yeah, it's difficult to have a short answer to your question.
Right.
Yeah, I guess, you know, if you observe some interesting phenomenon, let me know. Yeah. Oh, in the end of the day, electroplasticity is something that is practical. If you can demonstrate that electroplasticity is a useful technique, I think that's more important.
Okay. Thank you. Thank you very much.
Okay, so if you have further questions, I think Shiteng has the email, and you can probably send your question to him, and I think he will also I think he will also be happy to answer your question. And so last call, if any other attendees have any question, so please note us or just unmute yourself or raise your hand. All right, if not, so maybe we will wrap up our today's talk. So I will thank Ouyang to co-host with me for this wonderful event. I really appreciate Shiteng for coming here.
Thank you.
Yeah, this is our last talk for season 2, right, Jen?
Yeah, right. That's the last episode.
Yeah, this is the last episode for our
season for now.
Yeah, season 2 TMS Talk. So we probably will pause our talk for maybe 1 or 2 months, right?
Yeah, so I think for the next talk will be in August.
Yeah, so we will we'll have our talk next season starting from August. And thank you, everybody. Thank you for coming today, and see you guys next.
Thank you very much. Well, yeah, thank you very much.
Thank you.